Greetings. I'm Mr. French, and I'm coming to you from my classroom in Mount Pleasant, Utah. And these are topics 4.1 and 4.3, interpreting the meaning of the derivative in context, and rates of change in other applied contexts, non-motion problems. I decided to combine these two because interpreting the meaning makes more sense when we talk about the context that we are applying or examining these rates of change. So let's start by looking at some areas where rates of change become very important. One of those is in physics, when we look at motion. So changes in position over time are velocities. Changes in velocity over time are accelerations. And here's one that you may not have known. Changes in acceleration over time. That's called jerk. So each of these measurements are very important in physics, and they all have to do with rates of change. Another place where rates of change are important are when we look at changes in current over time in electricity. So changes in current over time, changes. Here's another. In chemistry, we're also very interested in rates, in particular rates of reaction, changes in concentration over time. We also look at changes in volume with respect to pressure, compressibility. What happens when we apply a lot of pressure to a piece of coal, for example? Other examples occur in biology. When we look at a change in population over time, the growth rate of a population, or the velocity of blood through a blood vessel with respect to the distance from the outer edge of the rim of the blood vessel. This is our velocity gradient. You can see how the blood flows faster near the center of the blood vessel than it does as it gets closer to the edge. All of these are rates of change that we can measure or examine through the lens of calculus. Economics is another place where rates of change, how things are changing, is hugely important in economics. We look at how things change in cost with respect to the number of items produced. Here, those changes, which we would normally call a derivative, right? Rates of change are being derivatives. In economics, we call that the marginal cost, the derivative of the cost function. And the change in revenue with respect to the number of items produced is the marginal revenue. Changes in profit, of course, is therefore the marginal profit. One day when you take an economics class in college, you will see a graph like this one over here, and it will all make sense to you. Here are some other places where change is important. We can look at geology. What happens in geology? Well, the flow or velocity of lava can be pretty important to know. In engineering, when we build a dam, the amount of pressure of water pushing against the dam varies or changes depending on how deep we go. And knowing just how strong that dam has to be at different depths, very important. In urban planning and design, knowing how populations change as we move across a state or across land, the density, people per square mile, there's a rate for you. Meteorology, weather. Well, air pressure. How does the air pressure change depending on our altitude, right? The air pressure gets less, so we need to know what kind of thrust we need as we go up, or what kind of pressure will be pressing in on our weather balloons as they go up. All very important rates, pounds per square inch. In psychology, there's another one. You've probably heard of the learning curve. How does our ability to learn new skills change over time, or after how many times we've tried something? We start out slow, then we start to accelerate our learning process, and then near the top, our learning process slows down again. Our amount of improvement per trial shrinks. Sociology, another place. How do groups behave? Well, this curve looks kind of similar to the learning curve, but it's actually an adoption curve for technology. At the beginning, very few people buy a new piece of technology, but then after a while, it becomes more and more accepted, and more people quickly acquire it until we slow down again near the end after a large percentage of the population has acquired the technology. So let's look at some examples. Right? So if a question asks for the units of a derivative in context, the answer is always a rate of change. Something one per something two, where the something one is the units of the output and the something two is the units of the input. For example, if the function g of d is a function measuring pounds of gold, g, as a function of the depth of the mine measured in feet, d, then the units of the derivative would be pounds per foot, output per input. The units of the second derivative would be units of the output per units of the input per units of the input, since the second derivative measures the rate of change of the first derivative with respect to the input variable. So the units of the second derivative for the above example would be pounds per foot per foot. If a question asks you to interpret or explain the meaning of a derivative, for example, g prime 40 in the above example, you need to be as precise as possible using both units, numerical values, and an expression indicating the number as a rate of change. G prime of 40 indicates how fast the amount of gold in pounds is changing in pounds per foot at a depth of 40 feet. Notice how we included all of those criteria. First, we talked about the rate, how fast it's changing. So there's our rate. Then we used the units for both output and input. We used the numbers, and we used the rate units. It's important to include all of those to get full credit for a question that asks about interpretation. Let's look at an example here. If a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes, then Torricelli's law gives the volume of water remaining in the tank after t minutes as V equals 5,000 times 1 minus t over 40 squared. What is V prime of 20? Well, to find V prime of 20, we would just plug 20 in for t. 20 over 40 is 1/2. And 1 minus 1/2 is 1/2. And 1/2 squared is 1/4. 1/4 of 5,000 is going to be 1,250. The units of V prime 20, well, the units of the output volume is going to be cubic gallons, or just gallons, right? Volume is gallons. And then our input was minutes. So our units are going to be gallons per minute. What information are we getting from V prime 20? This is the interpret piece of the question. So here's where we're very specific. We say that the instantaneous rate of change of the volume of water in the tank at t equals 20 minutes, measured in gallons per minute. See, we used the rate we used the time, and we used the units. Let's look at another question. Here we go. The function f of s measures the time in years that it takes for a tree to grow to a height s, measured in feet. What are the units of f double prime of s? Well, double prime. First, it's going to be output per input for the first derivative, and then per input again for the second derivative. So our output, the function measures the time in years. So that would be years for the output. That it takes to grow to a height s measured in feet. So the input is feet. So per foot would be our units. Years per feet, or per foot per foot. All right, there we have it.